In this video, we'll look at how to solve initial value problems involving systems of linear, inhomogeneous, or if you prefer, non-homogeneous, differential equations. For us, this will mean a system of differential equations of this form, where A is a 2 by 2 matrix of constants, and B is a column vector containing two entries that are also constants. As usual, we'll also impose an initial condition, something like this. We'll also impose another constraint on the initial value problem, one that will fuel our ability to solve it. Specifically, we'll assume that we can find an equilibrium solution U star. I want to emphasize that this won't be true of every system of linear, inhomogeneous differential equations out there. So, we're really only learning about solving a subset of possible problems in this video. Recall that an equilibrium solution U star is one for which U prime becomes 0 when U is set equal to U star. This means that we find an equilibrium solution by first substituting U is equal to U star and U prime is equal to 0 into the system of differential equations. The equilibrium itself is then found by solving the system of regular old algebraic equations that results. Once we've found an equilibrium, we use it to transform the system of inhomogeneous equations into a homogeneous one. To do this, we define a new unknown function, say the vector x of t. We define it as the original unknown function minus the equilibrium that we found. If we differentiate the new vector x and carry out a bit of simple algebra, we eventually find that it satisfies a linear, homogeneous system of differential equations. When we restate the initial condition in terms of the new unknown function, what we see emerge is a problem that we already know how to solve. To solve the given problem, then, we just apply the knowledge we've already acquired to first solve for x, then use the definition of x to express our answer in terms of the unknown function we were originally given. Let's now try an example. Suppose a drug is administered to a patient intravenously at a constant rate of 0.6 milligrams per minute. Let's say the drug is eliminated from the bloodstream at a rate of 0.002, where this is a per minute rate. Let's also say that the drug moves from the bloodstream to the target tissue at rate 0.007 and from the target tissue into the bloodstream at rate 0.003. Again, we're talking about per minute rates here. Based on this information, we'll devise a model for the relationship between the amount of drug in the bloodstream and time, and another for the amount of drug in the target tissue and time. If U1 of t is the amount of drug in milligrams in the blood at time t, and if U2 of t is the amount of drug in milligrams in the target tissue at time t, then our goal, plainly put, is to find these expressions. To accomplish this goal, we'll build a system of differential equations, then discover the model by solving those equations. We'll look at the bloodstream and tissue as separate but coupled systems. We'll then apply our experience with conservation laws to each system in turn to get a single differential equation for each. Let's first look at the bloodstream and think about du1 by dt. Since the drug is neither created nor destroyed spontaneously in the bloodstream itself, our experience with conservation laws says that du1 by dt will just be the inputs to the blood minus the outputs from the blood. Before we start throwing numbers down, though, let's pay attention to dimensional homogeneity. du1 by dt is a rate in milligrams per minute, and so the inputs and outputs that appear on the other side of the equation will have to have those same units. As it stands, though, only the intravenous input 0.6 has the correct units. The rest are missing milligrams. It makes dimensional sense, then, to multiply the remaining rates by some amount of drug. The correct amount in each case is found by following each arrow back to where it originated. So, 0.002 becomes 0.002 times U1. 0.003 becomes 0.003 times U2, and so on. It follows that du1 by dt is given by the following expression. We do something similar to get du2 by dt, and we quickly see that this system can be written in matrix vector form like this. This is a linear inhomogeneous system of two differential equations. If we assume that the patient in question has no drug on board at the moment the IV was initially administered, then we can add this initial condition. Let's now solve this initial value problem. We'll attack the initial value problem using the approach outlined at the beginning of the video. Our first step is to find an equilibrium solution to the system of differential equations, assuming, of course, that such a solution exists. To find the equilibrium, we set u of t equal to u star and u prime of t equal to the zero vector. We then solve for u star by developing a system of 2 equations and solving for the elements of u star. In this case, it's easy to see that the equilibrium solution to the system of differential equations we developed is the constant vector 300, 700. Now that we have the equilibrium solution, we define a new unknown function, x of t, as the original unknown function minus the equilibrium solution we just found. We've already seen that x must satisfy this homogeneous linear system of differential equations. It must also satisfy this initial condition. The matrix that features in the system of differential equations has two distinct real eigenvalues, lambda 1 and lambda 2. Associated with these are the eigenvectors v1 and v2. Based on our previous experience, we know that the vector x is equal to this, where c1 and c2 are constants whose values have yet to be determined. We find the constants c1 and c2 in the usual way. We set t is equal to 0 and use the information provided to us in the form of an initial condition to set up a system of 2 equations. The solution to these equations is the following. These values for c1 and c2 are then plugged back into our expression for x of t, bringing us to here. To get our final answer, we recall that, by definition, the original unknown function is our vector x plus the equilibrium solution u star. It follows that this vector u of t is the solution to the original problem we were given. Its first element, u1, describes the relationship between the amount of drug in the bloodstream and time. And its second element, u2, describes the relationship between the amount of drug in the target tissue and time. Let's recap. In this video, we encountered a method for solving a linear, inhomogeneous system of differential equations when that system admits an equilibrium solution U star. Our method required us to 1. Find the equilibrium, 2. Define a new unknown function using the equilibrium we found, 3. Realize that that new unknown function satisfies a homogeneous system of differential equations and that we know how to solve such a system, and 4. Express our answer in terms of the unknown function we started with. After quickly running through this 4-step method, we applied it to solve a modeling problem related to drug kinetics. You've mastered the ideas laid out in this video when you can do the following 2 things. First, you'll be able to solve a pair of linear, inhomogeneous differential equations when those equations admit an equilibrium solution. And second, you'll be able to extend your use of conservation laws to develop differential equations that describe the dynamics of coupled systems, just like we did in the example we explored together. Make sure to set yourself up for success by exploring the world of linear, inhomogeneous differential equations beyond this video lesson. Read, try the assigned problems, make up some new problems, and try some new problems made up by somebody else. You'll be amazed at how easy it is to get yourself where you need to go when you mix up your learning.